Pierre Pansu from Université will speak about large-scale conformal maps.
Thank you. It's a pleasure to join this program for 6 months. I'll try to be around as much as possible. And glad to interact with all of you. So this talk is in the geometric vein, kind of continuation of those by Lang and Schroeder yesterday, and it has to do with conformal geometry, and the idea is to perform conformal geometry on graphs and groups, which everybody in this audience should understand this goal. So conformal geometry, this started some time ago. This person, Gerhard de Kremer, it's the inventor of the Mercator map, planisphere, and his map was designed to be conformal. Conformal meaning that angles measured on the Earth are equal to the corresponding angles on the map. And so the idea was to help navigators to follow routes called loxodromics with constant, which make a constant angle with meridians. So that's a good property of these maps, but the drawback is that the distance distortion is huge, as all of us know. The Greenland, for example, appears huge on Mercator's map. So this problem of controlling the metric distortion of conformal mappings has been around since, let's say, the 16th century and actively in the 19th century. So conformal maps in 2 dimensions, when orientation preserving, are the same as holomorphic functions. So many results in classical function theory are expressible amounts to a distance distortion. So the most striking one is Schwarz lemma, the holomorphic functions of the disk to the disk, that is f of z less than 1. If it fixes the origin, then its derivative at the origin is at most 1. That follows from the Cauchy formula easily. And here is an invariant reformulation of Schwarz lemma. So now, if you don't assume that the origin is mapped to the origin, the suitable statement is as follows. The function decreases hyperbolic distance. And so a consequence is that holomorphic functions, when they are bounded and defined on the whole plane, they must be constant. Indeed, consider its restriction to a large ball. So it maps a large ball to a small ball, and so the derivative estimate at the origin is very small, and going to the limit, derivative has to vanish. And maybe you remember this theorem by Picard, that an holomorphic function defined on the whole plane cannot omit more than 2 values. This follows from Schwarz lemma, combined with some extra information, the fact that there exists a holomorphic covering map from the plane with 2 points deleted, from the disk to the plane with 2 points deleted. So composing a map to the plane, lifting in this covering gives rise to a bounded holomorphic function on the plane, has to be constant. So we'll see later that we use similar tricks in a large-scale setting. So this is the 19th century story of the metric properties of conformal mappings. But pretty soon, it's good to go to a wider setting. So in higher dimensions, what does conformal mean? Same meaning. It's a, let's say, a conformal diffeomorphism, that's a smooth map whose differential preserves angles, and this can be said equivalently as follows. Infinitesimal spheres, tangent spheres, are mapped to infinitesimal spheres. So then we see interesting conformal mappings. The stereographic projection that maps the Euclidean space to the sphere minus a point, or hyperbolic space being conformal to a ball, but also balls are not conformal to Euclidean space, the complete one. But this sounds nice, but it's disappointing because there are few conformal diffeomorphisms. A classical theorem of Liouville from the 19th century says that conformal mappings, even local ones in dimensions at least 3, extend to global conformal mappings of the sphere, forming this group, finite dimensional Lie group, the Möbius group. So conformal mappings in higher dimensions are scarce, and this led people to already to coarsify the theory. So this is a notion, quasi-conformality, that arose in 1928. Herbert Grudge produced this definition for diffeomorphisms. Say quasi-conformal means that infinitesimal spheres are not maps to round spheres but to ellipsoids of bounded, uniformly bounded eccentricity. So locally, of course, a diffeomorphism is always quasi-conformal, but globally it's a uniform property which may fail. So I choose not to give the more technical Grudge definition, which includes homeomorphisms, but let's continue with an example which is not smooth at the origin, but nevertheless globally quasi-conformal. It's the power map, Z to Zk, in a radial manner. It takes rays through the origin to rays, and it's a power map along each ray. And this is an example of a global quasi-conformal map of the plane. Now, Grudge theorems, his first results are metric distortion properties of quasi-conformal mappings, with in particular this consequence that you cannot map quasi-conformally a Euclidean ball to the whole Euclidean space. So he did it in 2 dimensions, but the arguments are the same in other dimensions. So and the proof is a quasi-version of Schwarz lemma. And it shows that the conformal diffeomorphism is Lipschitz, at least at large scale. So with respect to hyperbolic metric. So but I'd like to now to describe what happens at small scales as well, because this may, in order to complete this statement, and this led to this notion of quasi-symmetric mapping. So a quasi-symmetric map, it's a homeomorphism. Its definition makes sense for general metric spaces and maps. So it's a homomorphism that satisfies a certain distance inequalities, which is a bit hard to grasp, but I think the picture helps. So at each point x, consider an annulus between 2 concentric spheres. It is mapped into another annulus, and the quantitative measurement here is that the ratio of radii of the 2 spheres forming the annulus in the range are bounded independent on radius of the domain annulus and position of point x. this is the notion of quasi-symmetric maps. And the Grudge theorem at small scales tells us that a quasi-conformal map is quasi-symmetric. So from the global point of view, this class behaves exactly as quasi-conformal and conformal mappings. So quasi-symmetric, this is weaker than by Lipschitz. The prototype is the power map Z to the K, which is only Hölder at the origin. But it's nevertheless pretty close from Lipschitz. Now, I think of this as some kind of attempt to coarsify conformal geometry, but at some microscopic scale. And we, in group theory, we have already heard about this word of quasi-symmetric in the context of hyperbolic groups. This microscopic geometry, it lives on the ideal boundary. So on the ideal boundary of a hyperbolic metric space, we have visual distances. So here the construction is recalled. Ideal boundaries, this means geodesics emanating from a common origin O. And now these geodesics, they tend to diverge. And you have to go a certain distance r from O in order for the distance between the two geodesics to be some standard reference distance, let's say 1. And then you define visual distance between the endpoints as e to the minus this distance r. Right. So does not quite satisfy triangle inequality, but you can cheat, manipulate the definition in order that it be satisfied. So really have true distances. And now when you change the origin O, it turns out that these distances, they vary in a quasi-symmetric manner. So the identity with respect to two different visual distances is a quasi-symmetric map, at least, let's say, locally. So the notion of a quasi-symmetric homeomorphism is well defined on and between ideal boundaries of hyperbolic metric spaces. And it turns out that for hyperbolic groups, we really have some kind of equivalence of categories, that is, a quasi-isometry between hyperbolic groups extends to the boundary into a quasi-symmetric homeomorphism. And the converse is true. A quasi-symmetric homeomorphism of the ideal boundary admits a quasi-isometric extension between groups. So these metrics have a good quality. You can arrange that they be alphas regular. So alphas regular means that the volume of balls is the power of the radius. So what does volume mean? I don't need to specify. As soon as there exists some finite measure that achieves this measure is simply Hausdorff p-dimensional measure. So this quasi-symmetric geometry is kind of convenient and has tools, is rather rich, and so the traditional terminology is to speak of a quasi-symmetric gauge. I think this was introduced by Bourdon. The quasi-symmetric gauge is an equivalence class of distances which are alphas regular. And so such an equivalence class is well defined on the ideal boundary of hyperbolic spaces, especially hyperbolic groups. And this theorem for groups in some sense says that this microscopic kind of conformal geometry contains all the large-scale geometry of hyperbolic groups. Well, the classical terminology now, quasi-symmetric, is not exactly well suited. So quasi-symmetry, these quasi-symmetry properties of visual distances, it's kind of local. To make it into a global notion, you have to introduce the notion of a Möbius structure as Schroeder did it yesterday. So what we have is the proper word would be a quasi-Möbius geometry on the ideal boundary of groups. So the notion of quasi-Möbius maps was introduced by Vaisala some 20 or 25 years ago. Right. So we see conformal geometry is infinitesimal, but there have been attempts since the end of the 19th century to coarsify it, leading to this kind of microscopic conformal geometry, where the keywords are quasi-conformal, quasi-symmetric, quasi-Möbius. But the story is not finished, right? So I like to tell you another story, pretty different, has to do with sphere packings. So sphere packings means in Euclidean space, or in more general metric spaces, a collection of interior disjoint balls. The incidence graph of a sphere packing means when balls touch, so the vertices are, there is one vertex per ball, and you put an edge anytime two balls touch. And let me, following Benjamini and Schramm, introduce this definition that a graph is packable in Euclidean space Rd if it is exactly isomorphic to the incidence graph of some sphere packing of Rd. So the goal of this definition is to view a sphere packing as kind of a map of a given graph into Euclidean space with special properties. It's an unusual point of view on sphere packings. So there is a beautiful theorem about circle packings in the plane that says that every graph which can be embedded in the plane, planar graph, is packable in the plane. That's an amazing theorem which I imagine as a variant and some avatar of Riemann's conformal mapping theorem. Let me argue this point of view. So it turns out first that this Koebe packing can be computed efficiently numerically, and then I think it was Thurston who suggested the following procedure. So given some planar domain, then draw a part of the standard circle packing, equal radius circle packing of the plane, the part which is contained in the domain. And then this produces a graph. Possibly you add, you imagine that there is one circle at infinity, and so you add edges for the boundary circles, joining them to infinity. Now apply Koebe's theorem to this graph. So this, the point at infinity will contribute a big circle, and now to each of these small equal radius circles, there will correspond some circle here, but now with different radii, but with the same incidence graph. And you should view this picture as a map, a discrete map from that domain to the disk. And Thurston asked whether this procedure would, this discrete map would converge to the Riemann mapping. And this was later proved by Friedman and Hay. And this can indeed be used to provide numerical calculation of conformal mappings. It seems to me that there are plenty of software on the web where the conformal mappings are computed in this manner. Right. So you see, that that's really one way of thinking about Koeber's theorem as a discrete version of Riemann mapping theorem. I call this mesoscopic because now we are dealing with object of a standard size, not quite microscopic anymore. Well, furthermore, you perhaps know that Andreev theorem, which is the cornerstone of Thurston's hyperbolization theorem from the late 1970s, is a variant. It follows from Koeber's theorem. So you see, that's a good theorem. Now, here is so that's the two-dimensional story. So we know exactly which graphs are packable in the plane. In higher dimensions, essentially, very little is known. But Benjamini and Schramm came up with the following result. For instance, the grid in Rn, you see what I mean by a grid in R2, and the corresponding graph in higher dimensions. So this can be packed in Rd only if n is less than or equal to d. And the same for grids, analogues in an hyperbolic geometry. They can be packed in Rd only if the dimension was already less than d. And this already non-trivial theorem, and today I will kind of elaborate on Benjamini and Schramm's ideas. That's the idea. That's what the rest of the talk will be about. So what I want to do now is to provide you with a large-scale version of that theorem. And for this, I start from this idea of disk packing, and I will quasi and quasify it, right? I think this more or less answers the question that has been asked yesterday during Victor Schroeder's talk. So, what should replace a disk or a ball packing is this notion of blah 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 packing. So means you have 4 parameters there. So why? So what are these parameters? So R and S are bounds on radii of the balls involved in the packing. So now L is a scaling parameter. So I want to require that not only the balls in the collection are disjoint, but slightly larger balls, concentric balls, are also disjoint. So I want more room between the balls. And the integer n there, it's a multiplicity. It's there to allow for non-packings, for some overlap, but the number of overlapping balls, we want it bounded by n. So this adds some flexibility. So this multiplicity will play no role in the talk. It plays some role in the technique. You may pretty well ignore it. The important new factor is this factor L, right? Which allows to replace objects which are exactly spheres by objects which are pinched between a sphere and the L time larger sphere. right? And this makes things quasi and flexible now. And I will now introduce an unpleasant definition. So unpleasant because full of these parameters, these 4 parameters. So what does it say? So it says I want maps that come with a ball correspondence. So for each ball B in the domain, its image is not a ball. I want a ball B prime that contains the image. Could be the smallest ball containing the image, for instance, but need not be. And now I want that this map and this correspondence between balls takes packings, 2 packings, where the parameters L and L prime are there. So means, and the quantifiers are in the right order. So if I impose the scaling parameter in the range, I want to have a scaling parameter in the domain, which guarantees that these rather scarce L packings in the domain are mapped to less scarce L prime packing in the range. So, and I want this to work at all scales. You see the size of balls R and R prime will be large, and there is no upper bound on the size of balls, only lower bounds. So these R and R prime are precisely there to make the definition large scale, to ascertain that we manipulate only large balls. But there are nowhere an upper bound. Right? A ball has to be large, but can be mapped to arbitrarily large balls in the range. Well, it's impossible to absorb such a definition in a few minutes. Just take it as the idea that packings are mapped to packings with certain quantitative guarantees. So the kind of maps that satisfy these assumptions are quasi-isometric embeddings of spaces, one space to another. And the definition is designed so that the composition of 2 large-scale conformal maps is again a large-scale conformal map. So this definition, by construction, is a quasi-isometry invariant. It's not quite satisfactory because for me, the main feature of conformal geometry with respect to compared to metric geometry is that a ball of standard size or even large may happen to be mapped to something very small. And the requirement that we manipulate only large balls to be large scale prevents this. And so I fear that this definition might kill the spirit, the main flavor of conformal geometry. That's why if we let the size parameter in the range go to 0, so no requirement on size of image of balls in the range, then we obtain in fact a larger class which I call the roughly conformal maps, which seems to me more appropriate generalization of conformal mappings. So we'll try to, so this is the large scale, this is the category, the things that you can compose together. This is a notion in which both spaces, range and domain play symmetric roles, whereas there is an asymmetry in this definition here. So now I'll give a few examples of such maps. So turns out that all nilpotent groups admit such embeddings in some Euclidean space. That's the Aswad theorem. Aswad says that everything which is doubling, so that's the case of the nilpotent groups at large scale, can be embedded in Euclidean space in a way which is by Lipschitz after you've snowflaked the metric, so raised the metric to some power. Such maps are large-scale conformal. And another consequence of the same theorem by Aswad is that every hyperbolic group can be conformally mapped into some hyperbolic space, or to the isometry group of hyperbolic space. So this power map is large-scale conformal, but only for k bigger than 1 when it expands, because the k less than 1 when it's contracting, provided this is forbidden because you cannot contract too much with my definition. Too bad. So now, I must say that even for the smallest nilpotent group, I don't know in which dimensions it can be embedded into Rn. In fact, this is a problem even in the Aswad setting. And the same for in the hyperbolic group setting, a lattice of complex hyperbolic isometries. I don't know in which dimension it can be mapped in real hyperbolic space. So today I will merely give upper bounds. So it's very partial, but that's the only result I have now. And I will say that a certain quantity which sounds like a dimension must increase if you map conformally a space X to a space X prime, or a group G to group G prime. So which dimension is very different from one class to another class of groups. So in the nilpotent case, the dimension is simply the exponent of volume growth, which is not a big surprise. For hyperbolic groups, we have several notions of dimensions attached to them. There is one which is called the conformal dimension of the ideal boundary. It's the least Hausdorff dimension of Alfors regular metrics in the conformal gauge of the boundary. And there is another one which has to do with LP cohomology, which I will define later. And we know that the second one is always less than the first one. But often, in many examples, they are equal, but not always. And here is the theorem I can prove. It seems, yeah. So D2 is the larger one, and D1 is the smaller one. Yeah. So in this class of groups, in these classes of groups, so nilpotent or hyperbolic can be finitely generated or Lie groups. It's the same. So a large-scale conformal map can exist only if these kind of dimensions increase. So this sums up 4 different statements, since we can nilpotent to nilpotent, nilpotent to hyperbolic. You see the 4 combinations. I don't claim that any result like this is sharp, but for instance, it tells us that the Heisenberg group can be embedded in Rn conformally only in a certain range, and no way to expect that this will be the sharp dimension bound. But anyway, that's the only information I have. Now, one point which is maybe not clear, so technically the coarse embeddings, this is now a standard notion. Embedding is coarse if it maps points at a standard distance to points not too far and not too close, right? And so the typical example is a injective homomorphism between groups, right? So that's a very large class. So technically, they are not included in my in this notion of large-scale conformal maps, but the theorem applies to the coarse embeddings as well. And it seems to me, so David Hume convinced me, that there are not that many invariants that we know how they behave under coarse embeddings. So that's a useful result as well. And finally, if I really want to do conformal geometry, I was born as a geometer, not as a group theorist, you know. Then I want to study this larger class of maps, which here are large scale in the domain, but not in the range. So it's indeed larger, because you can compose any such map, roughly conformal map, by a quasi-symmetric or quasi-Möbius mapping, and it's still roughly conformal. And now it's, of course, the theory becomes of a very different nature. You can map infinite space to compact spaces. The prototype is the stereographic projection, or the Poincaré model of hyperbolic groups, in some sense mapping a group to its boundary. So these are examples of roughly conformal maps. So it turns out that among the 4 cases of the theorem, 3 of them apply to this larger class of maps. Right, so that's the catalogue of results I have to offer today. So I'd like to explain a little bit how one proves this. So let's introduce more of these ugly definitions with plenty of parameters in them. So the main trick of that theorem is to define an analog of the integral of the LP norm of the LP norm of gradient of a function. So what I have in mind is that when you take a U function and let's say on Rn, the nth power of the gradient, once integrate, this is a conformal invariant. If you change the metric on Rn conformally, infinitesimally, this doesn't change the integral. And so I want to use this trick for more general metric spaces. So I produce a metric notion substitute for this integral without any measure in it. How do I proceed? In some sense, I imitate the definition of Hausdorff measures. So I fix some exponent p, and I consider packings by balls, and consider the variation, the oscillation of the function on each ball, max minus min. Raise this to the power p, sum over balls in the packings. So I don't have a preferred packing. So I will take a supremum of these sums over all packings in some class, this class of LRS packings, where radius of balls are more or less specified, and you have this parameter of L that imposes balls to be rather separated from each other. This produces a number, and so sometimes I call this P energy. Sometimes this energy is finite, so that's easy to show for Lipschitz maps on all-force regular metric spaces, because you can then compare these sums with some volumes, some measures. And since, so this notion is not empty, and it will turn out that if we stick to positive values of R and S, and then the energies do not depend that much on R and S, and they do not depend very much on parameter L either. So the class of maps, quantitatively, you may ignore all these parameters around, which I will do from now on. Let's do as if we had a well-defined notion of integral of gradient to the P for any function on any space we are dealing with. So once you have this notion, there are a whole theory of associated notions. The modulus of a curve family. So these were the kind of tools that Grotch used in the early 1920s. So the modulus of a curve family, you consider all maps to a metric space and consider the images of your curve, and you want to minimize the energies of such maps, and you use these curves to normalize. Of course, the infimum of energies will be 0 if you take the constant function, the constant map. But if you require that each curve in the family is mapped to a curve of length at least 1, then you cannot minimize. The infimum need not be 0. This is, by definition, the P modulus of a curve family. And the typical curve family, so how should we think of P modulus? That's not exactly a measure on the space of curves, but nevertheless it behaves very much the same. So what we retain of this construction is the idea of almost every curve, that the curves of vanishing P modulus can be discarded. And now the typical curve family I want to consider is simply curves that go to infinity, starting from a point or from some bounded set. And this now this curve family, if its modulus is 0, I will say the space is P parabolic. If non-zero, it's non-parabolic, or P hyperbolic. I'll avoid to use hyperbolic in this setting. So it's the idea comes from the criterion that allows to distinguish conformally the plane from the hyperbolic plane. So the plane is too parabolic, whereas hyperbolic plane is not. Right? And this goes back to the 19th century. And it turns out that for finitely generated groups, we can decide which are P parabolic and which are not. This is a miracle, but it's not that hard, in fact. So P parabolic groups are only groups of polynomial growth, and provided the degree of growth is less than or equal to P. And this follows by some isoperimetry criterion. So isoperimetry prevents parabolicity. It implies a Sobolev inequality, which is a lower bound on the energy of a function in terms of of some LQ norm of that function. So isoperimetry, lower bounds on energies, and so goes against parabolicity. And now the isoperimetry, we know by theorem by Coulomb and Saloff-Coste that finitely generated groups have a rather strong isoperimetric inequality, except those of polynomial growth. So that's if you now combine with Gromov theorem, we know that this P parabolicity phenomenon will occur only for nilpotent groups. Good. And this is enough already to rule out large-scale conformal mappings, because by construction, this notion of energy is functorial under large-scale conformal maps. Right. So proper, of course, embeddings works as well. If you have a map, large-scale conformal or of course embedding between two spaces, if the range is p-parabolic, then the domain has to be p-parabolic as well. So this handles 2 over the 4 cases of the theorem. So the 2 remaining cases are when the ranges are hyperbolic, and now not at all p-parabolic. And then the argument is different. So the idea is to use the Poincaré model of a hyperbolic group. So what is the Poincaré model? So here is a picture of a hyperbolic group with ideal boundary. I fix some origin, then define some projection on the boundary as follows. Have a geodesic ray, Prof, and you're done. So it's defined up to some, it's a bit fuzzy map, but good enough for our needs. So this gives you the radial, so a map to the ideal boundary, and then you add simply the distance from the origin, and this gives a map from group to boundary of group times R. And this map is, in a suitable sense, a rough conformal map. So composing it with a large-scale conformal map gives again a rough conformal map, to which a more general theorem will apply. So the theorem is formulated here. This is pretty close to Benjamini and Schramm's theorem. So here the range, the domain is a space, a group, for instance, and the range is a compact Alforce regular space. So typically the round sphere, or the ideal boundary of a group, or this product. And so I assume the range is Alforce regular for some exponent q. Then if there exists a roughly conformal map, then the domain has to be parabolic, or if it doesn't want to be parabolic, something else happens to it. Its reduced LQ cohomology does not vanish. And I will define this cohomology in a minute. So now, again, I'm studying situations where you have a domain group which is either nilpotent or hyperbolic, and a range group which is hyperbolic, composed with Poincaré model. And when the domain is nilpotent, it turns out the nilpotent group have vanishing reduced LP cohomology for all P. So we are in the first case of the theorem. We'll have a constraint on parabolicity, and we know that exactly when nilpotent group is parabolic, and this will give the conclusion that the dimension increases. Now, when the domain is hyperbolic, hyperbolic groups are never p-parabolic, so we are in the second case, and we have to understand the LP cohomology of hyperbolic groups. And all this works because for which range of values of P, so any Hausdorff dimension of a metric which I am allowed to put here, and so the metrics I am allowed to put on the boundary is the infimum of the Hausdorff dimensions. By definition, is the conformal dimension. And there is a dirty trick to kind of get rid of this extra useless factor. so dirty that I don't want to say a word on it. Right. So this was this nice result by Benjamini and Schramm in the setting of ball packings. And the logic of the proof, I need to give more definitions. So this energy of functions amount to start with a function, and you remember as some oscillations. Oscillation means I take the function of two variables, u of x minus u of y, and take its supremum on a ball. This is the oscillation. And more generally, if I have a function of several variables, I can take its sup on balls and then raise to the p power sum over a covering, take the sup over a certain class of coverings, and obtain norms and a function of several variables. Let's call them cochains, Alexander's Spanier cochains. And so we have a cohomology theory of such cochains for which now we have norms. And the cohomology is defined for this space of cochains with finite norms. And reduced cohomology means you divide cocycles by the closure of coboundaries in order to obtain a Banach space. And so this weird definition turns out to be computable because the general principle says that this definition coincides with more traditional definitions in terms of differential forms on manifolds, for instance. So analysis can be used to compute these cohomology spaces. And the point that we will use is that for hyperbolic groups, there is no difference between reduced and unreduced. And by definition of this dimension d1, this cohomology vanishes for p less than d1. And it never vanishes beyond conformal dimension. That's a theorem by Bourdon and Pajot, I think. So you see, this is the only ingredient we need, the true calculation of cohomology which is needed for these theorems. Then should I say a word of the argument? I will certainly not go through the whole argument, but maybe the first steps. So the first step is naturality of P energy under large-scale conformal mappings. And so we applied to the identity map of an alphorse regular space. Think of the sphere, or more generally, of the boundary of a hyperbolic group. So this tells us that the map, large-scale conformal map itself, has finite energy. Now, more or less by definition of LQ cohomology, if it vanishes on the domain, it means that functions with finite energy, they tend to zero at infinity, or at least they tend to a constant at infinity. And so this, assuming vanishing of cohomology, I can conclude that my large-scale conformal map has a limit at infinity. And now I observe that the complement of a point in such an alphorse regular space is Q parabolic, so that there exist functions which pole at one point or 2 points with finite energy, but nevertheless tend to infinity at that point. That's a slightly complicated construction in general, but it works. And so I compose this large-scale conformal map which has a limit y with a function on the range which has a pole at y. I thus obtain a function on the domain which tends to infinity at infinity and has finite energy. But I just said that such a function must have a constant limit at infinity. Contradiction. So the rest of the argument, I won't give it now, amounts to replace vanishing of cohomology by reduced cohomology, and that's a bit tricky, and it's a place where almost every curve and parabolicity arises. Well, that's enough for today. So, in conclusion, I proposed a class of large-scale conformal mappings that can be composed together. So, does this constitute some category, some geometry? It's a bit misleading. It turns out that a map which is large-scale conformal in both directions more or less has to be a quasi-isometry. I know of no examples, and I have a partial result, including one extra assumption, that goes exactly tells this. So there is nothing like a large-scale conformal structure on a space arising from this discussion. So too bad, right? But nevertheless, as we saw, the result obtained indicate that the theory is not empty, and even the case of coarse embeddings is already a significant subcase. So I hope you found it interesting anyway. Thank you for your attention.
Question, comment?
I think I banged your head. There was
a question. So if you change Q into, so here the Q is the same. It's Q almost regular.
Yes. Yeah.
If you change NQ by NP for P different from Q, then everything will become.
Yeah. So you're right. When I said there exist functions with finite energy on a Q half-force regular space, you have plenty of functions which have finite Q energy. What happens for different values of different exponents? Energies are all zero or all infinity. It's very much like with Hausdorff measures.
Right. So, no more questions, then let's thank Pierre again.